Now we have an idea about finite automata. This is a finite automaton, and we'll now give a formal definition what actually is a finite automaton. And this is a special kind of finite automaton. It's called a deterministic finite automaton, and that's the automaton model we start with. If we have a look and we would like to give a formal definition of these things, there are several things we have to take into account. First thing is, as you see here, we have a set of states, the round things here. They're called states. And we have arrows between the states, and the arrows between the states, they're called transitions. Each transition is decorated with one or more letters, and there are two special states, the initial and accepting states. And now if we want to formalize it, we just have to collect all these things. So we define the automaton model is called deterministic finite automaton. And we say deterministic finite automaton, short DFA, is a structure. And in this structure we have first states, a set of states Q. We have an alphabet from which we take all the letters at the transitions. So we have an alphabet sigma. We have a transition function delta modeling the arrows. We have one initial state Q0, and we have a set of final states or accepting states denoted by F. So this is a structure, and where Q is a finite set of states. These states here, set of finite states, here we have 4, finite number. We have an alphabet. We have this delta. This is a transition function, and the transition function models the arrows between the states. So it's a function, delta, taking a state as input and a letter and yielding the successor state. So it's a function that computes for a given state and a given input the successor state. That's delta. And we have Q0, which is the initial state. It's this state here, in this case. And Q0 must be in Q, of course, must be a state. And we have a set of accepting states F. And with this formal definition, we have grasped the idea that's behind this picture here formally. And we need this formal definition if we actually want to work with it later on. So if we want to do constructions, construct new automata, we'll need this formal definition later on. The other advantage of having a formal definition is that if we are in doubt, for example, if there has to be an initial state, then we can just stick to the formal definition and look it up. For example, here we see there must be an initial state because it's required here. It's impossible to have an automaton without an initial state. Furthermore, if we have a look here at the transition function, we see that it should be a function, a total function, mapping every state and every letter from the alphabet to a successor state. This means that for every state and every letter that's in the alphabet, there must be exactly one successor state, not more, not less. These are all these things that we can directly check from the definition. So that's the use of a definition, to check these things.